So let's take a quick review of what we have on the agenda for today's demo measurements. We'll start out with just a review of the MarSurf CM products. The MarSurf CM family of products are confocal microscope-based surface metrology tools. These tools can be used for measurement of surface finish, microgeometry, micro contour, as well as other more advanced topography type of quantifiers. In my last webinar, we spoke about an update to the product line for 2020. That's the MarSurf CM Mobile in the center right bottom there. That tool for 2020 was updated so that it has the exact same sensor capability and the same sensor technology as the larger desktop and benchtop models. So maximum lateral resolution, maximum dynamic range, but now available on the shop floor or in the field via the MarSurf CM Mobile, which is our portable confocal surface metrology tool. Today, we're going to be working with the MarSurf CM Explorer. This is our compact desktop tool. It has 50 millimeter by 50 millimeter XY axes and 75 millimeters worth of travel in the Z range. So we're going to be doing some demo measurements with that tool today. The goals that I have for today's demo measurements, there's two of them. The first is to show you how the acquisition and analysis software function, how they perform. The second goal is to show you the breadth and variety of material types and material conditions that we can easily measure with this tool. To that end, we've selected a couple of different materials, a few different materials to look at. The first two measurements we're going to make are on steel parts. The first surface is a ground steel surface, very easy to measure. The second surface is a heavily media blasted surface. It's a steel coupon, very, very steep flanks, very faceted surface. That combination of very dark areas and very bright, highly reflective areas. It's fairly tricky for an optical tool to measure, and we'll show you how well we perform on that. The next measurement will be on an injection molded plastic part, a transparent plastic part, in fact, fairly complex geometry, and we on injection molded parts, we usually do geometry measurements or surface finish measurements. In this case, we're just going to show you a geometry measurement for this part. The next part that I'm going to measure, an alumina ceramic part, scatters light very, very well, doesn't reflect it too terribly well, makes it challenging for a lot of optical tools. Optical tools need a good reflected light signal, a strong reflected light signal, or they have a tough time measuring height. In the case of the confocal technology, even very, very weakly reflected or dispersed reflections are very easily measured with this tool. The final two measurements indeed are going to be mirror finishes on spheres. Combination of things here, extremely low roughness and very low contrast surfaces that we're looking at here. Low roughness, low contrast causes some technical issues for certain types of optical metrology tools. Additionally, we have a steeply curved surface here. That curved surface can also cause technical issues for other types of metrology tools. So we're going to put them both together and show you that neither of those two problems individually nor the combination of them really causes an issue for the confocal tool. So those are the measurements we're going to take a look at. I'm going to close down PowerPoint and jump over to the software. So this is the acquisition software. It's called MarSurf Metrology. It's our acquisition software for the CM product line. On the left-hand side, we have that's actually the live window. And what we're looking at in the live window, that is the V block that's actually on my surface. It's the ground surface of the V block. So it's a little bit scratched up. It's a little bit beat up, but that's my V block. And you can see it's live. I'm focusing over there. There's a lot happening on this, not too much. There's a number of things happening on the interface for the acquisition software here. We obviously don't have the time to do a full training of this software, so I'm not going to explain to you what every single icon means. But as I use portions of the software, I will tell you what I'm doing. So the first thing I'm going to do is I'm actually going to use our navigator here in the center. If you just follow my mouse, you'll see what I'm talking about. I'm going to use the navigator here in the center, and what that does is it does a very quick image capture of my surface. So it's actually using the stage to do a 3x3 image capture of the top of my V block. And I do that just to get an idea of where am I on the part, where am I going to do my measurement. And I'm currently doing that with the 5x lens. And there's a couple of ways we can tell that's the 5x lens. The most obvious one is here in step 1. It tells us that it's the 5x lens. 3200S refers to the field of view size, so it's 3200 microns by 3200 microns, 3.2 millimeters by 3.2 millimeters. So now I have in my navigator, I have an idea. I see, I'm at the edge of the V block. I have to make sure I don't try to measure over there. I'm using the 5x lens, but I really want to measure with a different lens, so I'm going to reach over and I'm going to rotate over first to the 10x lens, and you'll see we've updated here in step 1. And in fact, I'm going to move all the way over to the 20x lens. And again, you'll see it's updated here in step 1 to the 20x lens. And you'll also see my navigator is updated. So I'm going to focus a little bit better and move down a little bit to focus on the surface. Now that we've changed lenses. So there, I'm now focused on the surface again. And the red highlighted area here on my navigator window represents what I'm looking at here in the live window. So if I want to set up a quick measurement, I'm going to just kind of drag and drop and say I'm going to capture that area right there. I've just told the tool, simple as that, measure what's inside of that white rectangle. That's how I use my navigator. Now, as a rule, to get a quality measurement, a quality data acquisition out of this tool, all the user has to do is follow through these 6 steps and then hit the start button. You'll notice that as we go through the demos, I don't touch every one of those 6 steps every single time because many of them are not, it's not necessary to adjust them for each individual measurement. So for this first measurement, I'm going to go through all 6 of them, show you what they do, and then you'll see as we go into the other parts, I only will hit 1 or 2, or maybe even none of them before I hit the start button. So the first step we already talked about a little bit. This is where I would normally choose my objective lens, but on this tool I have automatic objective recognition, so the tool sees what objective lens is being used and it automatically updates this step. So I really don't have anything to do there. The next step is brightness. Right now I have it in auto mode because I'm kind of searching around looking for my surface, focusing. It's easier to be in auto mode, but when I'm actually doing the measurement, I usually switch over to manual. So we'll click it over to manual right now. The next step, the third step, we have to tell the tool what XY, what lateral field of view do we want to use. And I've already done that up here. I've already told the tool that I want to measure in this white area, and it's updated this field. So you can see it's going to do a stitched measurement. So it's going to do multiple measurements and stitch them back together, multiple fields of view, and then stitch them back together. So it's going to do 4 fields in the X direction and 1 field in the Y direction and stitch those back together. So this would be the first field it's going to measure, then it's going to measure roughly here, and then roughly here, and then roughly here, automatically move from one location to the next of the stage, and then at the end of collecting the 4 data sets, stitch them back together for a total measurement range of 3 millimeters by 0.8 millimeters roughly. The fourth step, it's a vertical scanning technology. That's the way it works. We're measuring height here. So I have to tell the system what is the starting height, what's the minimum height, what's the minimum height on my surface, what's the maximum height on my surface. I need to tell it where to scan, and that's what I do on this step. That said, for an easy part like this, I'm just going to tell the tool, do it automatically. You let the tool go find the high and the low points on the surface. The other setting on on this particular window that's important is I have my measurement range Z while stitching, and you notice I have shape tracing selected. What shape tracing means is that the tool uses the data set that it just collected to predict what the slope of, to recognize what the slope of the surface is and follow some contour or form on your part, so that it's a time saver, it's a convenience factor for curved or tilted parts. In step 5, this is where I set the distance between my vertical slices. So again, it's a vertical scanning technique. You can think of it like a CT scan. We're making multiple slices. And this is where I tell it how much space to put between the slices. This is the best quality is the smallest amount of distance between slices. Good quality is the coarsest slices. For a fairly rough surface like this, I am comfortable using the minimum or the minimum number of slices, the largest pitch between slices. So I set it all the way over to the left. Finally, I have to tell the system what to do when I'm done doing the data acquisition. The first portion of that is data processing. That's post-processing. If I want to use post-processing, I would check this button. Generally, we don't need post-processing with this technology, except for some special cases. But for the measurements we're doing today, no post-processing needed. We keep that unchecked. The final step before I hit the start button is I have to tell what report I want to send the data to. In this case, I have a pre-made report called steel ground for this particular surface. I'm going to choose that report. It's all set up for this measurement. All I have to do now is hit start. So first step after I hit start, it's quick range finder, we call it. It's finding the high and the low points within the measurement range. Now that it's done that, it's going to start the acquisition. Remember, I told you it was going to do 4 individual fields of view and then automatically stitch them together. It just did the first one. You just saw the second one flash past. It's going to start the third one now. There was the third acquisition. It's going to do the fourth one, and then it's automatically going to put those 4 square fields of view together to make a rectangular field of view. It's going to take that rectangular data set and it's going to send it over to our analysis software. That's what it's doing right now. So in the analysis software, I have my report set up to do some roughness measurements, some surface finish measurements according to ISO 25178 3D and ISO 4287 2D. The little bit of time that you saw there before the surface updated was that, or before the report updated, was that process running in the background, with those calculations running in the background. So what have we got in our report? At the top of the page, we've got this is our 2D topography view. So color represents our height. Blue is the very low heights. Red, you can see there's a little bit of red and white here. That's our very high height. And in the next image down, this is our photographic view, or our photomicrograph with full depth of focus. So our very high points and our very low points are in focus at the same time. And a very helpful visualization tool to see what our grind process looked like. So we can see it's really not a super high quality grind process. And there's a bunch of dents and dings on the top of my old V blocks, so we can really see the condition of that surface. And then finally, we have on this page, we have the interactive 3D view, so I can rotate it, I can zoom in and look at the different features from different angles. Just a great visualization tool. Great, we have lots of pretty pictures, but let's see some data. So on the second page, I have my ISO 25178, which is my 3D or my aerial surface finish parameters, or my surface roughness parameters. The most recognizable are SA and SQ. SA is your arithmetic roughness. That's very similar to RA in 2D. SQ is your 3D RMS roughness, very similar to RQ in 2D. On the right-hand side, I have my 2D or my profile surface finish parameters according to ISO 4287, and those are the parameters that most folks are familiar with, RA, RQ, and most folks are familiar with RZ as well. That is the 2D roughness. The way this works is the 3D roughness is being calculated from all of the data. Every data point that I collected, everything is being used to calculate, as one big group is being used to calculate these parameters. On the 2D side, I am telling the software, make a series of left to right profiles. I've got an area outlined here. I'm telling it, make all the left to right profiles in that area, and for each of those profiles, go through and calculate an RA value. So do that 800 times. There's probably about 800 profiles in that area. Go through, calculate RA 800 times, report back with a mean, a minimum, and a maximum. It can also do standard deviation and range, etc., but I just told it to give me those 3 parameters. So this is RA, the mean RA from the roughly 800 profiles, left to right profiles that I have in this selected area. So we have in one report, we have 3D or aerial surface finish parameters and 2D or profile surface finish parameters from one data set. From start to finish, the actual process probably only takes 30 seconds or a minute. I've been talking for 15 minutes, it feels like. So let's show you how quickly this can go without the editorial comments from me. So I'm going to go back to the data acquisition interface. I'm going to go up to my navigator. I'm just going to delete that because we're going to use a different part. We're going to reach over. I'm actually going to put my next coupon right on top of my V block. I'm going to move up a little bit to focus on that surface. And I'm really not going to do anything more other than just hit the start button now. So I'm going to leave all of my other settings the same. I'm going to let it find the high and the low points, same number of slices, same size measurement. I'm going to have it send it to the same template. The only thing I did was I just chose a different material. And as you watch in the background, you see the scans in the background, you can see that the material does look very different. It's very, very bright and very, very dark areas combined, and it's not these even grinding marks that we saw on the top of the V block. So we've got 3 of the 4 measurements done. It's completing the 4th field of view to stitch them all back together just like in the last measurement, and it's going to send it over to that same analysis report that we were just looking at. So you'll see again, it's the status bar is moving here. The blue status bar is moving. That means it's updating, doing all of the calculations. It's updating my report, and there we saw it just updated. We'll go back up to the first page of my report. And again, we've got it's the same exact format we saw before. It's just the new data set is in there. So we still have our 2D topography view, our photo micrograph, our full depth of focus photo micrograph, which again, if we blow that up, we can really see very different surface from what we saw before. Some very, very highly reflective areas and some very, very dark areas all around the surface from the media blasting process. And again, looking at the 3D, very, very different morphology on our surface here. And as such, we would also expect to see very, very different roughness parameters, and we do. If you were paying attention before, the roughness values, the SA and the RA were down around 1.4 microns. Now we're all the way up to 4.5 microns on those. So very, very different surfaces, but our process for measuring that surface was exactly the same. Now there's a little bit of, we'd have to pay a little bit of attention to our filter sizes for waviness, but that's for the next webinar. But basically, the process of acquiring the data and sending it over to the analysis report, identical and very easy. Once we had something set up, all we had to do was really click one button at that point. So that was 2 steel parts. I'm going to change over. I'm going to go back to the measurement software. I'm going to move my objective lens back to the 5x objective lens, and I'm going to grab my next part and put that on the stage. So I'm taking the coupon off, the steel coupon and the V block off, and I'm putting the next part on there. I'm going to jump to the ceramic coupon as my next part. So I've got my 5x lens, my brightness is on auto. I'm gonna move the head up a little bit to get my focal position, and this is actually the ceramic. And so what I've got here is it's the alumina coupon. It's an alumina coupon, and somebody has written on the coupon. So there's actually a pencil mark. There's a pencil line on the coupon, and we're going to take a look at that. Generally, this surface is a pretty poor reflector, so we wouldn't be getting a great signal on some other types of tools. But as you can see, we're getting plenty of signal back, and you'll see the quality of the data that comes out of the measurement as well. So again, I'm back to my 20x lens. It's really the workhorse lens. It's the lens that I like. If you're watching step 2 here, it's the lens. It's not just the lens that I like. It's a great lens because it has excellent lateral resolution. So it's sub-micron lateral resolution, and it's single-digit nanometer vertical resolution. I think it's about 5 nanometer vertical resolution for the 20x lens. So it's a really great lens. It's a workhorse because it has those great resolution specs, but it also has a fairly large field of view. In this world, it's fairly large. It's got a 0.8 millimeter by 0.8 millimeter field of view. So 20x lens again for this ceramic. My 6 steps. In this case, One thing I am going to just adjust, I'm only going to do a single field of view, so I'm going to go to step 3. I'm going to turn that down to 1, and I'm going to put it back to relative, which means I'm just going to grab what's on my live screen. Other than that, I'm just going to let the Z measurement, I'm going to let it find the upper and lower heights. The parameter I'm going to leave alone. I'm going to change the output because I have another template that I made for the ceramic part. So I've got a ceramic measurement. I'm just going to go over to the live view, and I'm going to check my intensity. Intensity looks pretty good. Intensity looks pretty good, so now I can just hit start. Does just like before, it's going to do a rangefinder to find the high and the low, the highest and lowest points on the surface. Now it does the acquisition. It's done with the acquisition already, and now it's sending the data over to the analysis software. This window pops up. It's telling me you changed that report that you had open before. Do you want to save it? I don't need to save it. I tell it no. And now it loads the ceramic measurement into the report that we've made specifically for that ceramic measurement. So here it is, status bar. It's just loading the newest measurement. So here we have it. So we see right off the bat, the format is a little bit different from the previous report, but the information is still the same. So I still have my 2D topography view. I've got my photo micrograph view, my full depth of focus photo micrograph view, and I have my 3D, my adjustable 3D view. Okay. What I want to point out on this particular measurement, very, very porous surface, but we really see where this pencil mark is. So we see this mark, and we look at it and we say, it's not really higher or lower. Here it shows up very bright, it reflects better, it shows up very, very brightly. But here it's really not higher or lower than the surrounding area. And we can look at that if we tilt the 3D view up on end. There's no bump where the pencil graphite has built up. It's actually just filled in. So the only thing we can really see here is how much smoother that area where we've written on the ceramic coupon is. We can see how much smoother that is. And that's exactly the analysis I've done on the next page. So we'll scroll down to the next page. And what I've done here is on the left-hand side, I have a map of the local root mean square roughness. So the local SQ. So in 50 micron blocks, I've gone through and I have calculated the SQ parameter for a 50 micron by 50 micron block, and it's been replaced by a color. A very bright color like white is a very high roughness. A very dark color is a very low local roughness. So you can see away from the pencil lead, we have this lighter blue color interspersed with some very, very light blue and even some white and oranges. But really where the pencil lead is, the roughness really does go down just as we expected it to. So we can visualize that very nicely. Around the pencil lead, we do see a decrease in the roughness. We can also capture that in even more detail if we want to. So what I did here is I removed the pencil area, the penciled in area, the pencil line. I cut that out and I calculated the RMS aerial roughness for that area, so SQ for that area. And then I went and I did the opposite. So I cut out everything except for the pencil area, and I compared the RMS roughness there. So not a huge difference, but definitely a quantifiable difference, about 80 nanometers difference in roughness on a 1 micron. So about a 10% difference in the roughness between the two areas. Why is that important? It's just the point here is simply that we can't really see a height difference there. If we were just to make a single trace and try to find a height difference in where that pencil graphite is, we're just never going to see it. It's tough to tell, but I've actually got a left to right profile extraction here, and I'm just going to drag that around, and you can watch this update. We can look at this and we say, oh yeah, there in the middle, there's something different. There's not quite as many valleys, it's filled in. But if you didn't have this chart on the left as reference, you would look at this and you may not. If you've seen a lot of profiles and you knew what you're looking for, you might be able to pick that out. But then we can move up here, and there's really not too much to see there. You would have a tough time if you just had this profile, was all you had to show me. You would have a difficult time convincing me that something different is happening here from over here. So the point here is there's several points here. The first point is, we have we have some additional analysis methods. So the analysis methods, how we handle the data, we have a bunch of different techniques that we can use to capture and quantify this behavior of the surface. This feature on the surface is the first point. We have many different techniques that we can use to quantify that. The second point, we can see, because we have a 3D digital data set, a 3D data set most importantly, we can start to see things in 3D that we might have never picked up just looking at the 2D data set. So that's the second point. The third point, and I forget about this, is this ceramic is actually pretty hard to measure. It's actually a pretty difficult surface to measure, but it's actually so easy with this tool that it becomes a triviality. It's really not, it's not the point anymore. But just the fact that we got data from this is actually is pretty exciting. So that, from start to finish, the actual measurement, again, a couple of seconds, and I've been editorializing for what feels like 5 minutes. So we're going to go over to the acquisition software again. Again, I'm going to move back to my 5x lens just so I have a little bit of room and so I can see what I'm doing. I'm going to take the ceramic coupon off and I'm going to put my next part on. My next part is going to be the injection molded part. And again, with this part, it's transparent plastic, injection molded part. So it's something that I'm always asked, oh, can you measure, can you measure polymers? Can you measure plastics? Okay, but can you measure clear plastics? And I always kind of answer a bit flippantly, and yeah, of course, obviously, yeah, we can do that. And I guess it's just because the tool does it so well, I don't realize that it can be problematic. So here's the part we're going to measure. In this case, I'm going to use the 5x to measure because I'm not really interested in my surface finish, my surface roughness. All I want is I just want to capture the geometry here. So I'm going to leave it in 5x. I'm going to make some other small changes to the measurement. You'll see things are a little different. XY field, I'm going to leave at 1. I can see the entire feature that I want to measure here. The Z I'm going to set manually this time, simply because it's going to be a very deep measurement. We're going to measure a little over 2 millimeters to get the entire depth here. So I set my Z measurement to manual. I come over here, I go into confocal mode, and now I'm going to focus up until I see the very top of my surface, and then I'm going to focus beyond that, and I'm going to set that as my upper limit, and you'll see my upper limit height matches my Z readout now. I'm going to move the head down. I'm going to focus down. Until I get to the very, very lowest feature down at the bottom there. So there it is. I'm going to stop real quick. I'm going to adjust my intensity down. That's a little too much light intensity. And then I'm going to keep going until I'm focused below this surface. And now I'm going to set my lower limit. And you'll see that updated. And my range is now about 2200 microns, 2.2 millimeters. So I've set a Z range of 2.2 millimeters. So I set my Z range manually. I'm also going to change something on the parameter here. I want to do a fast measurement. So I'm going to jump in here and I'm going to set my pitch to 10 microns. I'm not going to use one of the presets. I'm just going to set it to be a really fast measurement. Then I'm going to go into my output. And again, I have a pre-made template for my molded plastic part. And now all I have to do is hit start. It's not going to do the pre-scan. It's just going to jump right to image acquisition. So it's scanning the part, starts at the bottom, scanning up. Almost there, a little bit more to go. And now it's going to take that data set and it's going to ask me again if I want to save my previous work. I'm going to tell it no. And now it's going to load the new data set into the new template. There it is. So, as is always the case, we've got our 3 views here, and you can change this around. This is my way of doing things. When this software allows you to make a report or a template in any format you want, this is just my personal way. I like to start with these 3 views. In my 3D view, I also have the ability, I can overlay the intensity image on there, which makes for some interesting visualization as well. Kind of get an idea of what the high and the low surfaces look like and where they are with respect to each other. You can see we've got a little bit of noise in there from measuring steep flanks with the 5x lens, but we're really not too interested in in the flanks as much as we are these planes. We want to measure some of this geometry. So we'll jump back out of the full screen view. So what we really, as I just said, what we really want to know is what's the difference in the height between these different planes that we have on in this feature. So I've set that up down on my second page here. This is a great feature of the analysis software that automatically identifies groups of data that are have very close to the same height, and it associates them together and identifies them as a single plane. It does that via the surface height histogram for the data set. You can see that here. So it identifies the 4 different populations in the histogram, and I've told it, here's the threshold of height, so I want to include this little green area here. If I move it up too high, I can knock it out, but we do want that, so you can tell it, depending on what your analysis goal is, you can set that threshold height for the identification of a plane. How big does something have to be for you to call it a plane? I want everything. I tell it okay. And what it does is it goes to for each of the 4 planes that I've identified, it gives me a mean height, a minimum height, a mean height, and a maximum height. And it also gives me differentials between the planes. So between plane 2 and plane 1, so between the brown and the blue, it gives me a difference. It gives me a difference between 3 and 2, which is the green and the blue, and then finally between 4 and 3, which is the green and the pink. So it gives me the height deltas as well as any inclination difference between the two, or between the different planes. So again, very simple measurement, but a lot of data that we can pull out of it. We some geometry measurement on this clear injection molded plastic part. So so far we've done 2 steel parts. We did a ground steel part, a media blasted steel part. Then we jumped over to an alumina part with a pencil mark on it. And now we've done an injection molded plastic part. So arguably 3 different materials, but 4 very different surfaces. Now I'm going to go back over to the acquisition software. I'm going to remove the injection molded part, and I'm going to slide the first of my my spheres into place for measurement here. So the reason I have 2 spheres is because I thought the goal was to measure. I'm going to jump over to the 10x lens as I'm talking here. The goal was to measure a highly polished surface, and I thought that this particular sphere had a very highly polished surface. But when I actually went and looked at the measurement on this sphere, the highly polished surface wasn't really as polished as I thought it was. Excuse me. This is when as I mentioned earlier, when I'm doing my discovery work, my searching for my surface that I want to measure, I tend to put my intensity to automatic mode. Now here is the surface of that sphere. And this is what I was talking about. This is what I thought was a very highly polished sphere. Apparently it's been bouncing around in my sample box for too long. It's no longer very polished. So you've got these big check marks and a bunch of scratches and all sorts of stuff on here. Nonetheless, I figured, well, let's combine curvature, highly polished, and as well as some scratches and features on this particular part for the measurement. So we're looking at the 10x lens. Again, I'm going to switch over to my workhorse 20x lens, adjust my focus a little bit, also adjust the speed on my joystick. I'm going to slow my joystick down a little bit, and you'll notice that when I do that, the number of button dots that appear up there change. So I've got my joystick on nice and slow. Again, I'm just going to do a single field of view here. I really just want to capture the top of the sphere, or the apex of the sphere, if you will. I can set my measurement range back to automatic. I can let the tool take care of it itself. I want to set the parameter because this is a fairly fine surface. I'm going to adjust the number of slices. I want a fairly fine pitch between slices, so I'm going to adjust that. The final thing I'm going to do is, again, I'm going to check my intensity. So I do that in confocal mode, jump over to confocal. That also helps me center my sphere on the crosshair. So I'm going to check up a little bit. I'm going to move down a bit. Yeah, a little bit too much intensity, so I'm going to turn that down. And you can let the automatic do this. I prefer for spheres to do it myself. It's just a matter of habit. So now that I've done that, I come over to my output selection. Again, I have a pre-made report for spheres, and now I tell it, now that I've set it up for my sphere measurement, I can tell the tool to start doing the measurement. It's going to do the quick range finder to find the high and the low. There are the highest and the lowest points in the data set. And now it's going to go through. You'll notice the acquisition is a touch slower this time. Before it was racing right through the acquisition. It's a little bit slower now because we've got a little bit finer surface finish. We need that. We need to take a couple more slices. Done with the acquisition. It's going to transfer it over to the analysis software. As always, ask me if I want to save my work. I tell it no. And here is my data set. So again, same format as before, my 2D topography, my photographic view, and my 3D view. You can see we've got our check marks on the surface there. We really can't see them that well because the geometry in the topography views, because the geometry of the sphere is much bigger on scale than the geometry of the check marks. Even if we put it in intensity mode, we really can't see those check marks. We can't say much about them. The great thing is this is a digital data set, so we can easily take the spherical shape out, and that's what I've done on the next page. So on the second page here, I have taken the spherical shape out and calculated the radius, the best fit radius while I was at it. So I got 6.3-ish millimeter radius for this sphere. Now you can really see the check marks. And the other thing I've done here is I've calculated the 3D roughness. And again, SASQ, similar to RARQ. I was expecting an SA down in the single-digit nanometer range from this part. Obviously, we're not there. A lot of that has to do with these relatively large-looking check marks that we have on the surface are affecting my surface finish, roughening up the surface quite a bit. So what we're going to do on the next page, we're going to take a look at the geometry of those check marks, see how big they are, actually measure it instead of just looking at them and say, wow, they look big. So I can take my selection cursor, put my selection cursor across a couple of those check marks, and now I have got a cross section across them. I can take my cursors down here in my cross section, set them to a high and a low point on some of those check marks, and I've given myself a horizontal distance, height distance, and a least squared fit angle between the two cursors. So they are actually pretty small little features. They're only about 17, 18 microns from highest point to lowest point. Total height difference is only a micron, and the angle is just about 4 degrees, and it looks like a lot more than 4 degrees, but that's just because the scale on the vertical scale and the horizontal scale are very different. So again, from acquisition to data analysis, very quick, just a lot of me talking and explaining. But in this particular case, we did 3 different tasks, right? We were able to do 3 different tasks in one shot. We were able to measure the radius of the part, we were able to measure the surface finish on that ball, and we were able to go in and look at some of the defects on that ball and quantify those as well. So all 1, 2, 3 different tasks from a single data set. And you can set up this report to do 1 of those tasks, 2 of those tasks, all of the tasks as you like. So now I'm going to go back. I'm going to measure another highly polished sphere. This time it's actually a femoral head, ceramic femoral head, femoral head implant. Going to measure that, and again I'm just going to load it into this same template, and you'll see it's just going to populate all of the data here. Very quick process. So I'm going to remove this part, going to get the next part, put it underneath the tool. Switch back to my 10x lens just to make things a little bit easier on myself as I focus. So there is that's the surface. We can see already it's quite a bit better condition than the previous surface. I'm kind of moving over to the apex. I'm going to jump back to my 20x lens for now. I'm going to refocus again a little bit better. So now to find the apex, when you're measuring a sphere like this, you're usually going to have you're going to have this kind of ring-shaped focal pattern, and that's how I actually use that focal pattern to get myself centered on the apex of the sphere. So we're still in the 20x lens. For this particular measurement, I'm going to move over to the 50x lens. So again, I've got to refocus a little bit. Oops, gotten lost in space. So there's my 20x. There's my 50x focus. So now I'm focused, 50x lens is all set up. For the 50x lens, I am going to manually set my upper and lower focal points. I'm going to recenter again a little bit. Going to move up. Just fine tune my focus, move all the way up until I'm focused above the highest point, set that as my upper limit. Going to move all the way down until I'm again focused below my lowest point, set that as my lower limit. In the parameter, I'm going to bump it up again. I'm going to go for a higher number of slices, same sphere, analysis template or analysis report, and I hit start. So really there wasn't a lot to do. Once I know I'm doing a single field of view, I'm never even really looking at that step 3. Setting up my Z measurement, depending on what type of surface, a lot of times I can just use the automatic Z range. Sometimes I have to set it manually. The 50x measurement is a little bit finer measurement, so I like to do that manually. So I really, here is my other mirror polished perfect sphere that's not really a mirror polish or a perfect sphere again. So the first thing I noticed when I measured this part was if this were a perfect sphere, this ring pattern would be a circular ring pattern instead of a potato shaped pattern, a concentric potato shaped pattern. That indicates that we're just not spherical. The part isn't very spherical. The surface finish is very uniform, but it's not really mirror level, but it is very uniform. It's very, very fine polish. But the interesting thing to me was just the level of waviness on this spherical part. And we'll see when I move down to the second page. This is I've taken the spherical shape out or the sphere shape out, and in this case I've taken out a radius of 18 millimeters. But you see there's still quite a bit of height there. So we're going from about 0.5 microns down to 0.25 microns. So it's 250 nanometers of height difference between that this low kind of pocket and these two high pockets. That's a lot, relatively speaking. And if we look at the roughness, now I was really expecting single-digit roughness here, and we are seeing 27 nanometers. Still very low roughness. I was expecting 10, 7, 8 nanometer roughness. What that says to me is that we are still picking up some of the waviness component, what I would consider the waviness component on this surface. We're not really seeing the surface finish. And again, this is something for the next webinar where we talk a little bit more about how we do some of these analyses. But I'll show you real quick what my gut, not just what my experience tells me looking at this part, is I know there's still some waviness in there. So I'm actually going to go over to my workflow, and I have a filter built in there. I'm going to turn on a waviness filter, and I'm going to remove that waviness shape and just leave behind the surface finish. So now we've gotten rid of those large undulations, and we really just have the surface finish there. This is calculated in the wrong spot. I'll go through and quickly calculate the parameters again. So now this is these are the parameters calculated on the on this surface without the waviness in there, and you can see with the waviness we've got 28 nanometers SA, and here with the waviness removed we're down to 7 nanometers. So they're the same now. So 27 versus 7 nanometers, and this is more what I was expecting just by experience looking at the part and seeing the finish. So this was the waviness. This was the real true roughness of the surface. So quick summary again, we have using this same interface, really not doing anything more than a different click here, a different click there on one or two of the steps. We have covered 2 different surface finishes on steel, a curved steel surface with a pretty fine surface finish, a curved ceramic surface, the one that we're looking at still here, with a fairly fine surface finish, a flat piece of ceramic with some markings on it we've been able to capture, as well as some a piece of injection molded clear plastic we did some geometry measurements on. I was hoping to do a piece of paper and even a bone fragment. We could have done rubber, we could have done this, that, and the other things, many different types of materials, but I'm 44 minutes into the seminar already here. So the point is, the goal was to show you how the software functions. I think we got that one. You saw both pieces of software. It's a pretty fluid transition back and forth between the two of them. And I think I hope I did a good job of showing you the capability, the bandwidth that we have in terms of material type and condition that we can measure with a single tool with a couple of different objective lenses.